All right. So my topic was on 3D construction printing. My Facebook timeline post was about the patent in February 3rd, 1995, where Barak Koshnevic patented contour crafting, which is the precursor to 3D printing in concrete materials. So let me get into the presentation. So the conceptual beginnings for 3D concrete printing was back in the 1950s to the 1970s. A man named Victor Papanek thought of the idea of robotic bricklaying. Now, Victor Papanek was an advocate for responsible and very safe construction, especially the use of tools. This came about because in 1957-ish was the advancement of a efficient hydraulic concrete pump, which was used to pour out concrete into much larger construction sites. All these thoughts he published in his book, Design for the Real World, and this brings about the beginning of concrete printing. So the early techniques, both these techniques emerged in 1995. The very first one was by Joseph Pegna, in which he would use a sand cement forming technique. It would be placed on it and would use steam to very selectively bond layers, and this would allow for quicker, slower drying times and stronger construction. This didn't really take off because of issues and was mostly a theoretical technique. Barak Koshnevic instead came up with a technique called contour crafting. This came about at the time of early 3D printing with polymers and metals, and he made it as an alternative which was aimed to shape ceramic material. Contour crafting, although he originally used it for ceramic materials, he saw his potential for material fabrication, especially for things less than a cubic meter. It'd be a lot easier to just print something instead of making forms for, I don't know, like a billiard or something. So in 2000, he gathered a team at University of Southern California to begin studying how to expand the scale of his construction printing, which he aptly named 3DCP. So I have a short segment of a video of a TED Talk from Koshnevis in California back in 2012, in which he describes what contour crafting is. Let me make sure I put, share computer sound.
And there are about 400,000 injuries every year. Eventually, these translate into cost to the society and homeowners. Construction, the way it's done today, is very wasteful and generates a lot of emission. And because of all the different trades that are involved in there and the difficulty of the management process in construction, the process is pretty corruption prone. It is very costly and is always over budget. So what we have been focusing on, finding a solution to this problem. And our solution basically benefits from advanced technology. I named this process contour crafting, and it is essentially a way of streamlining the process of construction by benefiting from the experience that we have gained in the domain of manufacturing. In manufacturing, there's a process called CAD/CAM, computer-aided design, computer-aided manufacturing. A lot of things that you see are designed on computer and without any human interference are sent to the production machinery that automatically make those products that you use. So we want to scale up those processes and bring them to the realm of construction. This, of course, has been the desire of a lot of engineers and technologists. There have been problems, there have been difficulties in such a transition. Recently, there has been development in the field of fabrication. You probably heard about 3D printing of 3D objects. So contour crafting is basically scaling up 3D printing to the scale of buildings. What we are hoping to generate are entire neighborhoods that are dignified at a fraction of the cost, at a fraction of the time, far more safely, and with architectural flexibility that would be unprecedented. So the buildings that will be built, of course, will not be as homogeneous as these. Every building can be very different. They do not have to look like tract houses because all you have to change is a computer program. The architectural design is basically sent to the machine directly. This animation shows the concept. The material, which is cementitious materials, initially concrete, is deposited through a nozzle, and the building is built layer by layer. In the process, a lot of things can be done, including automatic reinforcement, automatic plumbing, automatic electrical network installation. And once the basic structure is done, there could be other automated processes that would do auxiliary operations such as finish work, tiling, and even painting using inkjet printers, the kind that print the billboards. So in the end, the whole building can be ready in an unprecedented time. We anticipate that an average house, like 2,500 square foot house, can be built in about 20 hours, custom design. The model that you see here is pretty simplified because I didn't want to make the animation difficult for my students. But you can.
All right. So I think that gives a pretty good overview of Coach Nevis's ideas on contour crafting and the basics of what 3D construction printing would be. So, did not expect that. So going on to the first generation of the technology actually being used, in 2003, Robert Soar formed a construction group in Loughborough University in the UK. So his group was studying on how to scale up existing 3D printer techniques. And in 2005, he got the funding and was able to build like an off-the-shelf printer. He used a gantry system, a generic concrete nozzle, and some motors to be able to move it around on tracks. And in 2008, they were able to get it functioning and move it towards commercial application. Also, in 2005, Enrico Dini patented D-shape technology, which is a very, that technology helps a lot in that it's the nozzle of the machines that are currently used. So it's the extruder for concrete. Nowadays, Loughborough University was able to get a commercial grade printer, and they actually licensed it to Skanska in 2014 for use. And now all this has moved on to controlled applications and actual projects. So I have like a little timeline video to summarize that and a time lapse of a construction of an actual building. So let me get to that.
Things started moving fast from there. The combined knowledge of BAM, Weber BMX, and TU Eindhoven led to the development of parametric computer models, optimized mortar mixes, and printing robots. Shortly after, in 2017, this resulted in the world's first 3D printed concrete bridge. This 8-meter-long engineering feat was placed in Gemert, the Netherlands, and was extensively covered by media across the globe. No more than a year later, the equally newsworthy Milestone Housing Project was revealed, a series of 3D printed houses in Eindhoven. With this, a whole realm of new possibilities opened up for the 3D printing market. Another big milestone followed in 2019, when BAM and Weber BMX opened the first industrial and commercial 3D concrete printing facility. Its 2 printing robots are now operational and working on projects on a regular basis. In the meantime, the factory intensifies the digitization of the complete design to realization process. Call this process digital manufacturing. So, what are they actually manufacturing there? One of its more recent projects was the Perfect Wave, a skateboard ramp produced for the Dutch Design Week in Eindhoven, demonstrating how the process creates freedom for designers. Currently, the factory is working on another first-in-the-world project, the longest 3D printed concrete bridge in the world. It stretches an unprecedented 29 meters. This project was commissioned by the Dutch city of Nijmegen and designed by renowned designer Michael van der Klee. It consists of separately printed elements which will be assembled on site. A daring and complex project which involves substantial experimenting and testing. 3D concrete printing is not just beneficial for big, audacious projects. For normal routine jobs, this technology can save substantial amounts of time, costs, and waste. Like the stairs we printed for ProRail. The parametric model allows easy adjustment to each unique situation and is delivered to site as a prefabricated, ready-to-place object, or the formwork of concrete elements for the train station of Driebergen-Zeist. This project resulted in an 80% saving on on-site labor and 60% saving on process time on site at no additional cost. Because concrete is only printed where it's needed for the construction, we're able to vastly reduce the amount of mortar needed. And since there's no more need to make molds or casts, we can minimize waste. As you can see, the possibilities of this exciting technology are infinite. We're determined to discover all of them. And we want to hear your ideas on how this digital manufacturing process could solve your project challenges. So come visit our factory and tell us what.
So that's a timeline of one of Contour Crafting's. So Contour Crafting actually became a company under Kosnevik, and this is one of their competitors from the Netherlands. So this is a timeline of their projects. And then a third competitor, Aviscore, actually is currently building houses and are working on low-income residences. Since they can build a house a day, they intend to keep working in Louisiana and California. So here's a time lapse of one of their bigger projects recently. So that's the end of my presentation on 3D construction printing and or 3D concrete printing. Does anybody have any questions?
So I have a quick question for you, John. You know, it looks like a beautiful technology, 3D printing, and also all other technologies that people have been talking about, automation, robotics. They look amazing, and from the data, they could save up to 30–40% of productivity. But why it still takes long for the industries to use them? What is the major bottleneck, such as scalability or safety or just the pure psychology?
I mean, this technology has only really been in production for the last 10 years, so a lot of it's still being fine-tuned. As you saw, that building in the most recent video was built by one small machine. I'm sure if you actually watch the rest of the TEDx talk by Koshnevis, he introduces systems on rails with multiple extruders to scale up and build apartment buildings with multiple printers going at the same time. I think right now it's just trying to get all the technology to where it needs to be and the safety standards, because while 3D printing concrete is good and very quick, depending on the area, if it's like here in Florida, with hurricanes or with earthquakes, you definitely need to make sure that the reinforcements are proper, since it's not a solid block of concrete anymore. It's 3D printed and hollow. So I think it's still in the growing stages. I imagine in the next decade or so, we'll see a lot more building, especially since we need to be able to build houses faster with the growing population. So that's my opinion on why it's not as widespread.
Yeah, I understand your point. So since this is a critical area, and so we do need a lot of validations. We need the data to show it's safe. It's cheaper, right? And before we can put it into like a broader use, right? And we need a lot of standards, building codes related to that, right? Okay. Any more comments from the class? So this is team
Also,
5, and team 5
team
just
5.
Yeah, just yourself.
Myself.
Okay.
There's only 9 people, and I'm the odd one out. So
yeah, we could team up.
So yeah.
All right, thank you, John. Yeah, let's move on. So if that's all, thank you. So which team wants to be the next?
Yeah, references, but not sure if you need
thank
them.
you. I really appreciate that. I wanted to mention that. I noticed that you actually added all the citation. Yeah, that's professional. Which team wants to be the next?
I noticed that you wanted sources on the thing, so I figured at least links at the end of the PowerPoint would be good enough.
Yeah, that's great.
All right.
So Remy, you want to be the next team? I'm sorry, you said you want to be the first.
No worries. If Kausak wants to go now, we can go, or maybe later.
Yeah, okay. Yeah, we can go.
Okay, sounds good. If you're gonna share, you can share.
Okay.
Gamma camera.
Okay, so hello everyone. This is team 1, and we are gonna be talking about gamma camera and how it's been developed during the time. Okay, next slide, please. So I'm gonna go over the background information and talk a little bit about the history, and later Kausak will go over the applications. Next slide, please. So first, let's define the gamma camera. It has like different names: gamma camera, scintillation camera, or Unger camera. Unger was the person who developed this technology. As is the name, gamma camera uses the gamma rays to provide scintigraphic scan, which provide a detailed images of body organs. And there is like a nice article and references. You can maybe later check that. So the person who developed this technology is Hal Unger in 1950s. And actually it was in 1957. He started like the first prototype at early 50s, and the first model was in 1957. So let's see the mechanism and about how gamma camera works. If we can't click the video, it's like 4-minute video show how gamma camera works. Could you please open the video?
Number 3, right?
it will be opening in YouTube, so I guess maybe you might share the screen of the YouTube or.
Who is sharing screen now?
Kaiser?
Okay, you probably want to, if you have a dual screen, you probably want to move the other screen here. And also, we cannot hear the sound of your computer. So when you share a computer, share the screen, if you go to the central, there's a button over there. You go there called Advanced Setting, and there's a checkbox called Share Computer Sound. You need to check it.
Okay.
Yeah. Oh yeah. So he sent it in case anyone want to. Okay. That's from John. Yeah.
Okay, thank you. So the video just showed us like general like concept how gamma camera works, and now if we can go to the presentation. So just like gamma rays, and it used like kind of filter with some like materials that filtrate these gamma rays and then translate it to an image. Can we go to the next slide? So after that, I think it's frozen. Yeah. After that, gamma camera has been commercially available since 1962, and then computers have been utilized to in scintigraphic scan since 1964. And then between 1965 to 1974, multiple centers or different centers start to developing their own computer programs. And after 1974, computers with incorporated nuclear medicine software packages become like commercially available. And there is like a nice articles, this reference number 1 goes over like how gamma camera started and developed commercial and available to everyone. I know like this sounds like more like a medical field, but after that we are going to discuss how we can use this kind of technology in our field. So can we go to the next slide? Last thing, gamma camera now has been used in the medical field, and it's become like more useful and more like accurate and more has like higher resolution. Can we click the video, and we will just play like the first two minutes from the video, just show how is the model like device is used in medical field. Yeah, if we can skip the introduction, like
the MIE
yeah,
is
so
a
this is the device.
gamma camera system with superb resolution and uniformity properties. This makes it suitable for the entire spectrum of nuclear medicine diagnostics. The robust open gantry requires little space due to its compact design and allows for a high patient throughput. The Syntron computer is a powerful data and image processing system that guarantees effective work due to its optimized user interface. The new gamma camera systems are designed in a complex process based on remanufactured equipment, new crystals, and a new computer system. The individual components are designed for different life cycles, many manufactured and the visible parts are painted. After the replacement of the worn parts, the complete system is assembled. The configuration and calibration of the detectors are essential for the quality of the image.
So this is how
in this sensitive area, passive components are cleaned and the detector electronics are tested. One of the most important steps is the renewal of the highly guarantee high image uniformity. Selected photo multipliers are used.
Yeah, go to like 2 minutes.
The variably angled support palette and the body contouring provide improved image resolution. The image information from the detectors is processed in the Syntron system, designed by MIE. Schematics, PCB layouts, source codes, and graphical user interfaces are developed in accordance with the functional specifications.
So like
with the aid of these developments, the Syntron computer system controls the acquisition, analysis, and processing of the image data. The entire examination spectrum can be conducted with the extensive software package.
Okay,
the software is designed for nuclear.
Now we are gonna go with Kausik to go over the application in the civil engineering field. Thank you.
Okay. Before, can you hear me? Okay. Before I introduce the application, let me show you a video about disaster in Japan.
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next: run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesanuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall into Kamaishi City. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan, and one of the 5 largest recorded in the world. More than 28,000 people are confirmed dead or missing.
So this is a picture of the Fukushima Daiichi nuclear power plant. The part of the nuclear plant was destroyed by the tsunami, and radioactive material, which very harmful to the human body, diffused from the damaged plant to entire Japan. And people lived around the plant, evacuate from immediately and lost their house. Also, people outside the area were threatened by diffused material. So the government decided to demolish the nuclear plant. The left-hand side is the before the earthquake. The right-hand side is the after the earthquake. And the project will be a long-term project like the Chernobyl disaster in 1986 due to the contamination of the building or area. For proceeding the project, there are 3 problems. The first is the workers' health. Accumulation of radiation exposure will eventually cause health problems like cancer. And the second is safety. To prevent radiation exposure, workers can do their job in a limited time. And last is management. To proceed and manage the project safely, the measurement of the radiation is needed. So from the above the reason, the gamma camera technique was the solution for visualizing and evaluating the level of the radiation of the buildings. This is called envisage. It is the gamma camera which is used in the ongoing project in the nuclear plant. The camera can visualize the level of radiation like this picture, and operate remotely and work in high radiation environment. So this is the benefit of this camera, and the people can see how much the building contaminated by radioactive material or radiation. So by combining robotic technologies shown on the video, this is a video actually working in the Fukushima Daiichi nuclear plant. The center of the image is the moving of the robot and the envisage. So the gamma camera is helping ongoing the project and saving human life in Japan. That's it. Thank you.
So basically, the gamma camera was used to detect the radiation level and to make sure it's safe for people to re-enter, right?
Yes.
Okay. All right. Thank you. Any more comments, questions from the class? Okay. If no, we're going to move to the next team. Thank you. Thank you, guys. So which team wants to be the next?
We can be the next.
Sure. I think
Hello, can you guys hear me? Oh, great. Hello, everyone. Me and Ibrahim are here to speak about the use of IoT data or the Internet of Things data in construction industry. Like the IoT or the Internet of Things was coined or invented in 1999 by Kevin Austin, but it is coming into use in the recent decade or the recent years. And we see that in construction industry, we have major problems where we are running behind schedule or we are over budget. And the main reason for this is because of the low productivity. And we have seen in this class, like over the few decades, our construction industry productivity has been constant, or I can say flat. And so to improve productivity, like we have made use of the IoT or the data visualization. And before we move further, we'll watch a video of how it is done.
PCL is a 110-year-old company founded in Saskatchewan. We operate in heavy industrial, civil construction, and buildings. Our customers are asking for new and competitive solutions to drive their own organizations. We need to embrace digital change to remain competitive and relevant.
It's not okay just to be a builder. We need to understand the development aspect in the early stages, the construction, post-construction, and frankly, how the building is being used by its occupants.
4 years ago, we had a four-pronged digital strategy that involved migrating to cloud compute, business intelligence and analytics, smart integration, and mobility. Microsoft and its Azure technology and platform have been a game changer for us relative to driving that strategy.
The Stantec Tower is an iconic project. It is the largest building outside of Toronto in Canada.
This is a LEED Gold certified building. We've relied on technology to implement our construction planning, from virtual reality, 4D scheduling, and HoloLens technology.
A smart building is a win-win for the owner, the operator, and the tenant. You're putting in the core infrastructure to make it flexible enough in the future. PCL created JobSite Insights, an IoT-based smart construction platform based off of Microsoft Azure, Azure Digital Twin, and Azure Maps technologies. It starts with instrumenting a job site with various IoT sensors, and then streaming that data in real time through the lifetime of the project.
The platform actually gives us physical hotspots in the building. They show red areas, which will drive us to go to that area and find out what the problem is. In a building this size, we're relying on our JobSite Insights platform to monitor the temperature, humidity, and pressure in 483 units. That's something that would normally be done by hand.
our cloud-based information is more readily available. It facilitates collaboration, so we can have all interested parties with the right information at the right time.
By gathering data from sensors instead of people, we can focus those people on more effective and efficient things that drive value back to our owner.
PCL spends $200 to $300 million a year on energy. With job site insights, we anticipate 15 to 20% savings just in fuel and electricity costs.
We have a significant opportunity to change the face of construction through the use of digital technology. Without the cloud, we would not have been able to do the things that we're doing today. As we continue to drive along our digital journey, Microsoft's going to be a critical partner for us in our evolution.
Okay, now we see that these construction industry problems where the productivity is low, we are using or partnering with the software industry to solve these problems. And this all like using the IoT sensors, which provide the real-time information of what is happening in the job site. So this kind of reduces the time the field team uses in manually taking out the temperature readings or the pressure or the humidity in the job site. So instead of that, like now they can use their valuable time working on a valuable tasks or activities. So like to use the large amount of data and making it available to the field team, PCL has collaborated with the Microsoft to prepare something called the Job Site Insights. And this pipeline diagram shows how the data collected using the sensors have been made into a readable format or available to the field team. So here we can see that we have Azure Data Lake where the sensor data has been collected in a data lake, and the data factory uses the raw materials or the required information and stores in the data factory, and it has been converted or transformed into a readable format using the Azure Database, and it's been stored in the Synapses Analytics. And these data bricks help in converting, like I said, helps in converting into transforming the raw IoT sensor data into the readable format, and it has been posted on the job site insight dashboards where it is available for the field team. And Ibrahim will further explain or show the demo of how it is being done on, like, how is it possible, or the demo show.
Hello guys. So can you hear me? Okay. So basically, this technology is depends on the Internet of Things, IoT, which use a group of sensors, and is actually almost sensors for everything, and we can use in the construction. So we can put actually sensors for measuring temperature, for humidity, for air pressure, or even for concrete strength and concrete temperature. For example, if we put a sensor for humidity, the sensors of humidity can alert us to humidity and other weather information that might have an impact on our building materials and the safety of workers. PCL company, they use this application and they have really good application for it. And here is a video. Let me share.
Users can navigate across various districts, job sites, and floors or areas to view the latest sensor readings available. Teams can be configured to give access to other employees and set up alerts or alarms. Alerts and alarms are set on sensors or groups of sensors. Thresholds are set to get alerts if sensors readings go out of these bounds. These alarms will send alerts to the employees through various email methods such as text messages or email.
The great thing about IoT is that there's a sensor for everything. JobSite Insights supports many different types of sensors. Typical run-of-the-mill sensors like temperature, humidity, and air pressure, to more construction-focused sensors like concrete strength and maturity, as well as pipeline pressure and valve states. The first benefit of having all these IoT sensors is that no more manual readings need to be taken anymore. Before, job sites that needed to ensure their environments were controlled had an employee go from area to area, physically taking measurements. The second and more important benefit, though, is that it gives us greater control over the quality of our final construction product.
So here you can see one of our demo job sites with a few simple sensor types. Employees can open the application to see the current environment of the job site from anywhere and determine if they need to physically go to locations if anything seems off. On this application, any sensors that have active alarms will show up in red. Alerts will have also been sent to the employees directly so they can act as soon as the alarm is triggered. A good example of this is on job sites where millwork is being performed. This work must be done and kept in a controlled environment to ensure temperature and humidity are within design thresholds. If these values do fall out of range, employees can act quickly, preventing damage and additional costs to our company.
A common problem when working on towers in the winter are pipes freezing and bursting, which can cause water damage to units below the burst pipe. Employees now can be alerted to the problem and address it quickly, or they can take preventative measures like closing a window or adding heaters to the rooms. This simple act can prevent large amounts of rework and additional costs to the project. Since job sites are constantly changing, sometimes it's not feasible to plan for every possible risk. During construction, it's easy for water to find its way into areas it's not supposed to go. And that could be due to heavy rains or melting snow. And rather than installing and then removing pumps over and over again in areas that need water protection as the construction progresses, we can use flood sensors to save the project money by allowing them to only install temporary water mitigation systems as needed once they're notified of water in a particular area.
So all these alarms can be viewed and tracked in the JSI application itself. Alarms will show up in red, as you can see here with this one demo device, and users can deal with them in real life, and then once they're done, they can go back to the application and clear these alarms to ensure that we know that the issue has been dealt with and nothing is outstanding, and we're not going to have any further problems there. If the device goes out of bounds again, we'll get another alarm, and we can make sure that further plans can be implemented to make sure that nothing's going to go wrong on our job sites. So now you're just getting a quick view into the JSI application itself, and I'll switch over to JSI Analytics, and we can have a look at the historical data JSI and its sensors have generated. So the Power BI dashboard offers a view into aggregated summaries of the data, along with detailed data down to each individual sensor reading. The main dashboard you can see now shows the available sensor types. Users can set the time span of the data they would like to see, as well as selecting different job sites that they want to view on this first page. Further slicers are available on an Options tab to filter specific areas or devices if needed.
Each detailed page provides an in-depth view into a particular sensor type. On this particular temperature page, there's a gauge that shows the range of values that has been experienced by the sensors, along with whether any of those values have fallen out of the thresholds that have been set. This page allows project teams to quickly review and identify any problems. The line graph displays trends which quickly highlight any anomalies that may have occurred. And teams actually use this dashboard extensively to ensure environmental conditions are met and sensitive areas are monitored. On a construction site, like I said before, where things are constantly changing, having this information readily available to teams allows them to respond quickly and make informed decisions.
One of the ways Job Site Insights has directly improved productivity is being able to monitor concrete strength and maturity once it is being poured. If teams know exactly when the concrete has cured and is ready to be built on, construction on that can start early. This saves days off the schedule, reduces equipment and labor costs, and ultimately makes the projects more profitable. Another way Job Site Insights has proved its value is when we need to provide proof that the construction environment conformed to specifications. If millwork is cracked and the clients are claiming that environmental conditions are the cause of the problem, we have all the historical data necessary to show that we did, in fact, maintain a proper environment. Warranty work and claims can end up costing a lot of money after a project finishes, and JSI Analytics can minimize these costs. There are many other use cases for JSI Analytics and JSI itself as the system continues to expand. I hope that this gives you a quick look at how we can use Azure and Power BI to help our business.
Okay, so this is one of the applications from a BCL company. And this is an example from the sensor inside the concrete. It shows the temperature during the days. It's really good. And also one of the sensor also can be used is some of them can be wearable. The workers can wear them, and it has many features, like also they can measure their temperature. They can also measure their even heart rate, which is also good for safety. So can anybody tell me what are some of the benefits from using the sensor in the construction? No one? Okay.
I think this will enable faster response, right? So if something is going wrong on the job site, instead of waiting for it to become a bigger problem, they can react really fast. And also, I guess I saw the sensors also have the geo information, the location information. So it's probably easier for the construction professionals, engineers, or maybe facility managers to find the right place, fast. And also with this cloud computing function, I guess we can also have some remote intelligence. Maybe it's easier for us to share the real-time set data with the technician without bringing them to the job site. They can just check all the information and see what's going on. So that's my understanding.
Yeah, and like during my internship where I was working on a heavy civil project, we had activities like pile driving or excavation and stuff. So we had to monitor the vibrations such that it doesn't affect the environment or the structures around us. So we had to monitor the vibrations in real time. So we had to install the vibration monitors so we could get alerts if it went over the threshold, and we could stop the activity and minimize the effect or the any disaster it would have caused. And also, like professor told, we do have geotags which can be put on some materials which are very expensive, or the equipments which are very expensive, which might get stolen, and we could track them with using the geolocations, and we'll be able to find where it is located exactly. That is one of that.
Yeah, I also want to point that having the Internet of Things is actually a very popular concept, but it's very difficult for construction because, like I mentioned earlier, construction sites are usually dynamic, and the installation, maintenance, and also the telecommunication infrastructure for construction jobs that can be extremely more difficult, right? Than having an IoT solution for manufacturing plant. So that's why I have seen some research directions having, for example, some sensors embedded inside the concrete. This part of the reinforcement, but also the sensors can detect the tension and also temperature. It's passive sensor, which means when you send a radio to it, try to read the data, you also power up the sensors. So that's actually some very interesting solution. And also the remote sensing technologies are also more popular, for construction, such as using camera view imagery, and some human carrier sensors, for example. So I think that's actually really good points for people to investigate, what kind of unique sensing network or IoT solution should be used for construction.
Yes, thank you, Doctor. Also, additional to what you mentioned, Doctor, some of the benefits, they can also increase the safety of worker, and they can increase the productivity. They also can increase, they also are safer for time. So no need to send an employee physically for measurement. They can measure by themselves, and even some of them can fix the problem by themselves. Also, they can be also safer for money. Yes, they are difficult to set them up, but they could be safer for money. The technology helps monitor construction site and uses data to predict patterns and prevent problem rather than focusing on actions when something goes wrong. I think this is all about our technology.
All right, thank you guys.
If anyone has questions, please go ahead.
All right, thank you guys. Thank you again. So we have one team. How about this? Let's finish that one team and take a brief break, and we will come back and finish up the big data and continue the big data discussion. All right. So I think what we're missing is team 4. Do we have team 4 here?
Yeah.
Okay. All right.
Yes, we do.
Okay. All right.
So I'll be sharing my screen.
Sure.
So yes, you can start.
Okay, so for our presentation, our topic is exoskeleton. Basically, exoskeleton is a kind of motorized or unmotorized machine which is made from metal that is built to fit on a person's body. And this machine was usually created to multiply the strength of the wearer. Rohit? Okay.
You want the video?
No, not the video. Can you open the September 1965? This is the
yeah.
No. Open the.
On the, you mean on the
No, September 1965, not this one.
Just a moment.
1965, the timeline. You are on the wrong year. Yeah, September 19th, 1965.
It's a
September.
Oh,
sorry. My bad.
Okay, so basically this machine is created to multiply the strength of the person who wears this, and it facilitates proper body mechanics. Also, from the construction point of view, it is easier to lift objects and can ease the strain on the body. Around 1965, this guy and the General Electric started to develop a full body exoskeleton just to increase the user's strength to help them lift the objects. And at that time, it started using in medical industries and also in manufacturing industries, but it came in construction industry in late 2014. And yeah, so there is a question, why usually people will wear the exoskeletons? So basically to reduce the stress put on the body while they to perform certain tasks and all. And also they have been used in labor intensive fields like the same construction and the manufacture to reduce the injury rates and assist in lifting and moving of heavy objects, and also to provide a strong support system for handling large machines and objects. There are 4 factors such as innovation, technology, safety, and efficiency. So these all factors have been leading the industry transformation, driving construction forward faster than ever. Unlike the advancement like autonomous equipment, BIM, drones, systems, so exoskeletons are a wearable technology that could make work safer, improve careers, and make employee management more efficient. Can you play the video?
Yeah. Oops. Sorry.
Advantages of animal locomotion with issued to Gompertz in 1814 is a three-legged walking robot carrying heavy weights placed high above the base of support. The device is operated by compressed air and carries its own power supply and controls. Robots. The locomotion is provided by the air cylinders representing the extensible legs. At various points in the walking cycle, it is necessary to prevent rotation of the leg about the foot plate. This is accomplished by pressure-actuated clamping cylinders placed at the ankle joint. The second robot is developed to investigate the feasibility of a powered exoskeleton for providing locomotion to non-ambulatory persons. The machine is designed for one-directional walking, and the motion pattern for all the joints is coordinated by cams mounted on a single cam shaft. The exoskeleton interfaces with the patient at a steel-reinforced fiberglass corset, which is designed to support his weight with minimum interference with vital functions by gripping the abdomen just below the rib cage. The corset is then supported by leg brace frames formed from welded steel tubing. Special care is taken to fit the leg brace frames to the patient's leg without restrictions or binding. Power is supplied by a 1/3 horsepower, 7,000 RPM DC motor mounted in the power box located on the back. Hydraulic and worm gear speed reductions, along with cams, rocker arms, and coaxial cables, generate the kinematic and power requirements to move the leg braces in a pre-designed walking pattern. To be useful for ambulation, the machine must also be able to provide sitting, climbing stairs, and stepping over obstacles under the patient's control. This can be accomplished with the help of computer control. The third walking machine was then developed to study the feasibility of a computer-controlled, multitask-powered exoskeleton for paraplegics. It is an extension of the previous walking device and provides computer-controlled, multitask capability under the patient's command. The different joints are powered by hydraulic actuators whose servo valves are driven by the operational amplifiers of a hybrid computer. The motion patterns are digitally stored in the computer, and the different actions can be executed at different speeds by activating the input control switches, which are mounted within the reach of the patient. Although a large hybrid computer was used in the developed prototype, the system is designed for control by a microcomputer no larger than 4 inches by 4 inches by 6 inches to be carried in the power backpack. The ambulation task capability in this prototype are walking, sitting, standing, climbing stairs, and stepping over an obstacle. This is slow motion execution of these tasks. First, you see slow walking with a short stride. Now the exoskeleton is sitting from a standing posture. Now it is standing up again. And this is the act of stepping over an obstacle. This illustrates the motion of the different joints in the act of climbing steps. The climbing is done one step at a time, and the patient has to activate the system for each step. Each joint in the exoskeleton is equipped with an angle sensor, and all the signals during any act are fed back to the computer to ensure that the actuators are performing as instructed, and if any error is detected, it is instantaneously corrected. Is a safety precaution and is instructed to relax the leg when moved by the actuator. The first executed act is a slow walk. The first part of the act is an initial stride, and when the command is received to stop the walk, a closing stride is automatically executed. The exoskeleton is now helping the subject sit from a standing posture. And now you see it help him stand from the seated posture. Actual executed angles are shown in these. Besides demonstrating the feasibility of powered exoskeletons for paraplegics, the developed prototype can be used in physical therapy to provide controlled exercise with graded assistance and to teach those with some muscular strength to walk again.
Okay, so this was the use of exoskeleton in 1965, but in around 2014, exoskeleton came into the construction industry, and there were many types of exoskeletons which are using now, which are like contractors are using nowadays, such as the mounted arm exosuit, back support exosuit, and arm support limb, crouching and standing support, and whole body suits. Now, Rohit will continue with the 2014. It's September 2014, Rohit.
Can everyone hear me? So I have an important question for the class. Like, why should we use exoskeleton on the first place? Can anyone explain me? Can anyone?
It might reduce the physical stress on a body.
Exactly.
And it's kind of safe for the say.
But what's the main factor? Like you are going to be a project manager, right? So what are you looking mainly into your construction field? Like what are you trying to avoid?
I mean, avoid safety hazards and improve productivity.
Exactly. He got the right point. So basically, exoskeleton, as my fellow said, that it's a sort of machine-made skeleton which is attached to a human body, and it powers you to do work with smoother functions like lifting and everything, and you can hold on to heavy objects for a longer time. So basically, this whole system was founded in 1965, but getting it into construction, it took around 5 decades for it. So here's a short video explaining what is the main importance of exoskeleton in construction.
To deliver power without pain for professionals who work with heavy tools. We wanted to take the next step with something more mobile made for smaller hand tools. So we created the Exo Vest. You put the vest on like a backpack, then strap in your arms. Turn on the lift assist and you're ready to go. The Exo Vest uses springs to lift your arms with 5 to 15 pounds of lift assistance per arm. The kicker is it's all mechanical. No batteries, no cables. And it weighs under 10 pounds, so you can wear it comfortably all day. The Exo Vest is perfect for a variety of overhead applications, like manufacturing, overhead drilling, laying pipe, and cutting and grinding. ExoWorks is sparking innovative change in the industrial space, providing power without pain. We can't wait to see what you'll do with it.
So guys, I have another question for you all. Like, what's the most important thing that we as a construction field people are lacking in construction? Like, what are we lacking on basically?
Maybe technology improvement. Technology improvement in construction.
Yeah, but like we are not up to the scale in terms of productivity, like as compared to other sectors, right? So basically, there's another video which explains how exoskeletons.
The rising cost of safety due to on-the-job injuries is killing our productivity, and that's where the ExoWorks aerial system comes in. With the patented zero-gravity arm, the use of heavy hand tools becomes almost effortless by rendering them weightless. We decided to put the Exo Zero-G arm to the test to see if it could save time and money on the job site by getting the work done faster and protecting the worker from injury and strain. We gave the workers 2 identical drilling and chipping tasks. Dwayne will use traditional methods, while Ed will be assisted by the Exo Zero-G arm. We will be monitoring the heart rate, time, and progress as both workers complete the task. The results are impressive. The Exo Zero-G enabled worker finishes all the tasks while the other worker becomes too exhausted in the process. With the assistance of the Zero-G arm, the worker completes the task faster and with significantly less effort and fatigue. So what if you could complete your heavy hand tool task faster with better accuracy and less injuries? Now you can with the ExoWorks aerial mount system.
So these are few of the benefits of using exoskeletons on site, and to be precise, more and more contractors are getting into this particular gist of using it. And it is said that by 2023, 33% of contractors will be engaged in using some variables which will be useful in terms of increasing the productivity. And like even right now, it has been observed that using variables on such as exoskeletons on site could be beneficial for social distancing as well, because it's one of the prime aspect which we are focusing right now. So yeah, this is the future we are looking forward. So that's it. Any questions?
Just a quick comment. I think this is the use of exoskeleton is profound for the construction industry.
I cannot hear your voice, Professor.
Can you hear me now?
Yes, we can.
Okay, yeah. So it's actually yes, it does improve productivity. Does make it safer. and healthier for the construction worker, but it also could potentially change the industry because of, it can broadening the population of workforce. Think about that. Usually it is considered that females are not suited for like a heavy labor task, but with exoskeleton, we can broaden their participation. And maybe for somebody like for disabled group, they might be, for the first time, they also might be able to work in this industry, right? We are facing a significant shortage of labor force in different regions. And the use of exoskeleton will definitely make that different. And for different professionals, maybe your body capacity wouldn't be a consideration anymore. That will make it's easier, right? So I guess so the impact of exoskeleton will be profound and impactful. But also one thing confused me a lot, not just exoskeleton, but all the technologies. Maybe this is my last comment for this Facebook project presentation, is we have seen a lot of technology started development in the 1960s, 1950s. And fundamentally for the past 6-7 decades, we didn't see significant improvement in the technology. But why still so slow in terms of technology adoption? Like you play the video of the first exoskeleton in the 1960s. It looked amazing at that time. And I bet, the people at that time were thinking about, oh, we probably could put this in use, in the next 5 years, but still we haven't seen that happening. So actually that's my question, something for you guys to think about, why the adoption of new technology is so slow.
Okay, Professor.
Yeah. All right, that's all great presentations, guys. So any more questions for this team 4, right?
Yes.
Yeah, team 4.
Any more question? Okay, if no, let's take another 10-minute, let's return, 7-minute break. Let's return at 6:35. Okay, guys? See you at 6:35. All right.
Okay, Professor.